All right. In this class, I just want to take you to some mathematics that at some point I feel maybe you don't need, and at some point I feel maybe you need. But this intuition, once you understand this intuition for gradient descent and you understand the intuition for cost function, then you are very much good. But just for emphasis sake, I just want to show you the mathematics for how we relate gradient descent to cost function. So basically how gradient descent affects cost function. So that you are going to see here. Right. This is our linear model regression. If you remember, h of x equals to theta 0 plus theta 1x. This is our cost function. J for theta 1 and theta 0 equals to 1 over 2m summation of our predicted minus our actual value all squared. If you remember that. And now this is our gradient descent, right? So repeat until convergence. You remember, this is what repeat until convergence means. Keep repeating, keep repeating, keep repeating until we get here, until convergence, right? Right, so repeat until convergence. We have our j theta is assigned to j theta, which is the former value of j theta minus learning rate and the derivative of j theta 0 and j theta 1. Right, now let's see how we can insert. See, we have j theta 0, j theta 1 here. We want to insert this into gradient descent, right? So that's just basically putting, so we call this putting gradient descent cost function. Right. So what we want to do now, so I need you to write this out all over again under this topic, right? So what we want to do is now is that so write out this, right? Write out this and write out this. What we want to solve for is this derivative term. We know what alpha means, but we want to solve for this. So let me write this out, right? Because I want to insert this, your j theta, I want to replace it with what we have here, right? So I want to solve for this, right? So let me just intentionally write out j theta j, right? This is a tick dot into the formal value of theta j minus learning rate alpha, right, into the partial derivative d theta, for this is theta j, into j theta 0 comma theta 1, right? This is our gradient descent. This is our gradient descent. Now our cost function on the other hand is j into theta 0 and theta 1 equals to 1 over 2m. Don't forget, m is the number of training examples, right? Into summation, we have m here, into summation of h of x minus y all squared, right? So we want to solve for this derivative term, right? We want to apply gradient descent to minimize our squared error cost function. Let me write that out for emphasis sake. I want to apply gradient descent. I'm sorry, this gets boring, but you need to get through the boring stuff to know what you're doing in machine learning, right? So to minimize our square error cost function. Right, so that we want to do, we want to apply our gradient descent to minimize our squared error cost function. This is our squared error cost function. So we want to just replace what is here with what is here, right? So very quickly, okay, so very quickly. So what we're going to have is, let me bring this down. Let me bring this down. So I'm going to have d theta, d theta, j multiplied by j multiplied by this, right? So instead of writing j theta, I'm just write what we have here, multiplied by 1 over 2m right, into a summation. I should have m here. So a summation of h of x minus y all squared. Right? This basically is, if I want to replace my h of x, remember that my h of x, remember that my h of x remember that my h of x equals to theta 0 plus theta 1 x. That's what we did. That was our first, right? H of x is theta 0 plus theta 1 x. So we're going to insert this into h of x now. So our formula is going to be d theta j times 1 over 2m into a summation of theta 0 plus theta 1 x, right, minus y all squared. Minus y all squared. Right, so this is what this gives us. Now to figure out the partial derivative, for theta 0 and theta, let me just use q for theta and theta 1. So I'll just write, I'll just write out the partial derivative for you. I would not prove this, but if you want to go through the proving, you can. There are a couple of YouTube videos that prove this for you. So what we have is for j theta. So for j theta or for theta 0, right? We have j we have J equals to 0 equals to 0. This will give us an assignment. This is a tick dot. All right. This will give us the theta into J theta 0 theta 1. This will be equal to, so for theta 0 now we're going to have 1 over m into a summation, right, of h of x minus y. This is for theta 0. Now for theta 1, we're going to have j equals to 1 to give us, sorry, this was theta 0. This should have been theta 0, not theta j any longer. Did the theta 0 because we are solving for theta 0 now, right? So this would be d theta 1 theta 1 into j theta 0 comma theta 1 is going to give us 1 over m into a summation over m into a summation. We have m on top here. A summation of h. We have a subscript theta here. H of x, right? H of x minus y. All in a big bracket, right? Instead of having the square there, we'll now have times, this is a tick dot, times x, right? So this is what we mean by solving, this is what we mean by solving for theta 0 and theta 1 simultaneously. So I just showed you the maths for what happened here. I just showed you the maths for what happened here, right? So we solve for theta 0 and theta 1, we move to the next step. Solve for theta 0 and theta 1, move to the next step. Solve for theta 0 and theta 1, update, move to the next step. This is the math of what happens, how we fit cost function to gradient descent. So solve for theta 0, solve for theta 1, update, solve for theta 0 again, solve for theta 1, update. This is what happens here, right? So this gives us another converse function. Let me draw the converse function now. Or let me write it out in more simple mathematics. Okay, let me first write it out in more simple mathematics. Let me write out in more simple mathematics. Hold on. So writing out gradient descent now. So this is gradient descent. All right, gradient descent algorithm for linear regression. Now that I've fit my cost function to my gradient descent, and this is our final formula. All right, so gradient descent for linear algorithm is let me first write repeat until convergence because that's very important. I'm sure you understand what repeat until convergence means, right? So you keep repeating until you converge at either of the local minima, right? Repeat until convergence. Then we have right, repeat until convergence, then we have this like this, right? So we have something like this, right? And we have theta 0. Then we have our assignment attributes equals to theta 0, the former value of theta 0 minus learning rate alpha. So we are bringing back, we took out this and we used this to get this, right? So we are bringing back our gradient descent, right, in full. So we have learning rate alpha into 1 over m, right? Remember, we had this equals to learning rate alpha. Then we simplify this to get this, right? So we have learning rate alpha into times 1 over m into a summation. We have m here of h of x, the bracket is x minus y, the bracket is y, right? Then we have theta 1 into the former value of theta 1 minus learning rate alpha into 1 over m. Then we have a summation of h of x, right? Bracket is x minus y, bracket is y. Then close this bigger bracket into x, right? Then we close our, right? So this, once again, is what we mean by update simultaneous updates, right? So update theta 0 and theta 1 simultaneously. Right. So at the end of the day, this is what let me see if I can draw what we will get. Let's see. Just to give us something like this. Right. We have something like this. We have like right, right. So we have something like this, right? And then our concave structure would be, we'll go from something like from here to here, then move from here to here, from here to here, and then come from here, and then we have something like this. Right. So this is what our plane looks like, right? Of course, where we are going to is our global minimum. So we are looking for, so this operation, right? Update. So let's imagine we start from somewhere around there, right? Or we start at theta 1, theta 0, somewhere around there. We can start at anywhere in our plane, right? So we keep updating gradient descent, upgrade gradient descent, upgrade it again. Choose your small learning, choose your perfect learning rate, upgrade the gradient descent, upgrade it, right? Till we get to a point, our global minimum. So this is a convex function, right? It's called the convex function. It's called the convex function because of the shape of the curve. And of course, this is called the global minimum. And to give you a better intuition, right? When you get to your global minimum, this is what we have our global minimum. This is what we have our global minimum. We have a plane where we have a graph, our usual graph now, our linear regression graph in 2D. Right? And then we have a strong line. So being at our global minimum is where our linear regression hypothesis gives us the strongest fit. So let's say we have our data this way, this way, this way, right? This way, 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 right? So for example, starting at a random point on this plane gives us a situation where we would have our hypothesis giving us something like this, right? And then as as your j theta keeps reducing and keeps finding minimum, right? So let's say this is one step in learning rate, then another step, then another step, then another step, then another step, then another step. What's wrong with this mouse now? Right? Then another step, then another step, then another step, then another step, then another step. And at the step where we get to our global minimum, then we have a perfect fit, right? So this fit is the point where we had the global minimum, right? Right. So this is where our global minimum is. This is where we had our global minimum. And just for emphasis, this is where our y equals to h of x. Remember, we talked about that here. Right? This was the situation we had here, where our y was equals to h of x. Our y, if you remember, our y is the price that we had in our data, and our h of x is our new prediction. Right? So at the point where our y equals to h of x is where we want to have our global minimum. That's where we want our j theta to be 0 if possible. Right? So that's what we have down here. Right? So that's going to be the end of this class. Cost function and gradient descent. So we've just finished the topic titled linear regression with one variable. In the next class, we are going to be looking at the intuition of linear regression with multiple variables. So thank you. I'll be expecting your questions.